guys, I have a mic because I'm recovering from sickness, and then I DJ'd at Crab, and then I yelled into the mic a lot, so now the voice is also even more gone. So, you know, I'm gonna wear a mic, but I'm also gonna show you how I can manipulate my voice with different things. So, basically, let's see.
You can start.
What did you say?
No.
Okay, so basically, this is like an all-inclusive overview of what sound engineering is as a whole, and it's going to be a lot of information that probably none of you are going to hold on to all of it, but I'm going fast through this because there's a lot to get. This is like a whole semester-long course that I could be teaching, but you know, I don't get paid to teach that, so I'm not going to teach that. But there's a lot of different information here, so if you hear anything that you are like, I want to know more about that, ask me after and I can go more in depth about it. And there's going to be different things that different people are interested in. So we're just going to go start. We're going to start with like why sound engineering is important. And the first thing of why it's important is sound quality, which is how the audience is able to feel the different instruments on a stage if it's a band and understand the separation between instruments. Clear and well-balanced audio is essential for a live event's success. Sound engineers eliminate distortion and feedback and all the things like that to make a performance a lot more enjoyable. Audience engagement is important, like if you're at a concert and you're listening to the music and it sounds like this, you can't really sing to it, right? Because you can't really hear the words necessarily what verse we're on. So things like that are what audio engineers are focused on. Performer confidence. If you've ever seen a concert, they have like monitors on stage or they have headphones in for them to hear themselves and the rest of the instruments so that they feel confident when they're performing, either playing their instrument or singing. Communication clarity. In corporate events where you, like basically the the all-campus symposium that we just had, that's technically considered like a corporate type event where there's a bunch of speakers. That type of event, it's really important to, I realize I'm talking loud again. When I normally teach, I talk loud and then I lose my voice, but I'm already losing my voice, so I'm going to talk quieter. It's really important to be able to have the audience understanding what people are saying so that they don't get frustrated. Atmosphere creation, this is more like theatrics and sound design. You're able to create and morph the soundscape in the space to make you feel like you're immersed in something. Consistency, every single night that a show is performed, the sound should be the exact same. When an audience member goes to a show, one night they should be able to come back in like 2 weeks and it should sound the same. It shouldn't be completely different. Safety and regulations, all sound engineers have their safety regulations knowledge so that they don't have cables hanging around and people tripping on it. Things also like rigging, when you put up big speakers on like poles or fly them up in the air, you probably want to know like what you're doing so it doesn't drop, possibly. Technical problem solving. A lot of sound engineering is figuring out what's wrong. So like there's always going to be things that are wrong all the time and you need to understand all the things that we're going to go through to be able to solve those problems. And production value. If something sounds good, it's better, basically. Okay, so what are we learning here? I kind of broke it down into these different topics right here, and we're going to go through them pretty fast because there's not that much time. So we're doing fundamentals of sound, sound reinforcement systems, mixing concepts and signal flow, signal processing, mixing techniques, live event setup and troubleshooting, mixing different types of events. If you're interested in specifically any of those, tell me at the end, and I can actually send you videos on those that are not by me. They're just YouTube videos that are really helpful that I've sent to other people to learn those things, because sometimes I don't want to sit down for like a 2-hour conversation. So I can send you like a 40-minute video. So what is sound? Does anyone know what sound is? Yeah.
Collection of frequencies.
Yeah, it could be a collection of frequencies. Sound is like a lot of things, but basically I sum it up in sound is air, which is not really, but kind of, because sound is the vibrations that in our world, they move through the air. Technically, if you go underwater, you can also hear sound, but it moves differently because of the, because it has different vibrational properties inside the water. But to me, in this world and in all of our work Most of the time, sound is air, kind of. Frequency, amplitude, wavelength, phase, and timbre we're going to go through right now. So frequency is the number of vibrations per second, and that's measured in hertz. So if you've ever like played an instrument, you know there's like a tuning note. That note is A, and I'm going to play you that A, which is 440 hertz. So this is the sound of A. Is anybody like sensitive? Your ears are sensitive. My ears are like sensitive, but like in a kind of a good way where I can like pick out different things. But if anybody's gonna like, I'm not gonna like play dog pitches, so that you're gonna be fine. But this is A, so this is 440 hertz, and that means that every single second there's 440 complete vibrations in a wavelength. With higher frequencies corresponding to higher pitched sounds, and lower frequencies correspond to lower pitched sounds. And this is a sine wave, so that's like the purest sound tone that you can get. Amplitude is the intensity of the sound wave measured in decibels, which to you is probably going to mean how loud it is. So decibels, if you're familiar with it, is basically a scale that we can measure the loudness of something. In sound terms, we don't like to say volume, because volume can mean like a bunch of different things. We don't really, it's basically an unspecific way of saying something's getting louder, because you can talk about gain, you can talk about output loudness, many different things. So volume's not really a good term for us. But wavelength is the distance between 2 points in the sound wave, and it's inversely related to frequency. So if I play you 440 hertz, which is this tone, you're having 440 vibrations per second. And then if I make it lower, and I play you 309 hertz, actually this is 302 hertz, the wavelength got longer and the frequency is lower. Polarity. So this is basically where a sound wave is corresponding to another sound wave. So you see like where these things are, right here, they're like not aligned. Basically what happens with these is that they're negating each other where they're not equal. Does that make any sense? It's easier to see than this one. This is like a basically complete opposite. So this sine wave is going like this, and then this one's starting halfway through that sine wave. So every single time it hits the peak or the trough of the sine wave, it's canceling each other out. So if you have headphones on, headphones bad, because you hear both in individual ears. But if you were in a space standing at the exact right position in between two speakers, and you were listening to this on the left side and this on the right side, you'd hear absolutely nothing. So I'm going to show you exactly what that means by giving you an example of phase cancellation, which basically I'm going to play that at 440 hertz. And you're going to be able to walk around and you're going to hear, if you've ever like been to a, I don't know, somebody was DJing, they have like a phaser button that goes and all that stuff. That's basically creating this type of cancellation within the left and the right side. So I'm going to play 440 hertz, and feel free to stand up, and if you move around, you'll be able to hear the phase cancellation. So I'm going to unmute. And if you listen to this and walk, yeah, you have a question?
Where's the stereo? Like where?
We have a left and right here. So the door is actually blocking the right. But if you walk around, you'll hear that it's like a little wobbly, right? So if you just walk, you're going to hear that the sound waves are actually canceling each other out in different locations in the room. Are we all hearing that or no? I'm crazy. We're hearing that? So basically, if you were the exact math point in between these two speakers, you wouldn't hear anything because they'd be canceling each other out. But it's hard to do that because this one's pointed at the ceiling, that one's pointed toward the back wall, and then all the sound is bouncing around the room, so we're technically hearing, it's impossible to get that perfect cancellation in a non-perfect environment. Did we get that? Am I explaining that well? Okay. Next slide. Timbre. Timbre is like the unique tone of every single sound source. So if we look at, we're going to look at this graph right here, and I'm going to click this. I'm going to talk into this mic, and you're going to be able to see that there's a lot of different frequencies popping up on the screen. It's not just one sine wave like this one was. So you see how that one's, it's a little bit extra, but you see how basically there's one tone, and you can see on the scale that this is right around 400 vibrations per second. When I talk in the mic, there's a lot more than just one thing popping up, and that's due to resonant frequencies and air noise. So every single tone that you hear, when you put it into a space, it creates resonant frequencies, which are like basically frequencies that all contribute toward the sound of your voice. So I can kind of go through what all of these mean. If you want to, oh, maybe I should lower the volume possibly, right? So that we don't die.
Yes, please.
Oh, good. Okay. So I'm going to put this down a little bit. I'm going to mute that. And if we listen to how I'm sweeping through the frequency band, you can hear that the lowest point in my voice, somewhere around like 190 hertz. So this is like the low section of my voice. And then if we squeak up to here, this is where like the middle section of my voice is. And then if we go up to here, this is like the high mid section. And then if we go right here, this is like where the crispiness of my voice is. Except I'm like recovering from sickness, so my crispiness is kind of like gone. But that's where the crispiness would land. You can kind of hear like my and all that type of sound, right? So all that crispiness lies around my 6K range, and every single person's voice is going to look different. So you want to talk into the mic, Jay?
Oh yeah, sure.
There you go. Watch his frequencies.
Hey, how's it going?
Hold on, let me raise the volume.
My name is Jay. That's Ethan. I don't really know.
You can see that his resonant frequencies
Hi.
are in a different place. And if you talk now,
Hello.
you can see that they're all lower. And you heard that in your ears too, that it's a lower voice, right?
Hello. Hello.
And you can see where those frequencies are, they start higher. Oh, magic. Timbre. So each individual voice has its own timbre, and the timbre is the characteristics that make up that unique sound, based off of frequency, wavelength, and all the stuff we just went over. Okay, we're done with like sound basics. That's kind of like theory of sound. You generally won't need to know exactly all of that ever, but you need to know that to figure out certain things like understanding the frequency spectrum. Human hearing goes from 20 hertz to 20 kilohertz. That's 20,000 hertz. So it's actually kind of smaller than that, and everybody's range is slightly different. But generally, you can hear from 20 hertz to 20 kilohertz. Anything below that, human ears can't process, and anything above that, human ears can't process. But dogs can, which is why they react like that. I'm dying, guys. So, sound reinforcement systems. I've split this into 4 different things. We have the source, which is right there. I just had the mic in my hand. The source, and then we go to the processing, which is the front of house. It's not pictured in this, but this is like where this console would be. The processing, and then we go to the amplification, and then that comes out to the output. So what does that look like for like in simple terms? Basically, you have a mic, you plug it into a mixer, which is going to tell it how loud you want it to be, or like what frequencies you want higher or lower based off of whatever space you're in. Then speakers, like if you just have a woofer, a speaker woofer, which is like what's inside these things, they need power. You can't just send it audio signal at what we call mic level or line level and expect it to generate power. We need something, which is this amplification unit, to basically multiply that signal by thousands of watts. And we can technically simplify this by getting a powered speaker. So this right here, this just has an XLR cable plugged into it, which is just a normal mic cable. And then we basically plug that in, and then inside this unit, it has its own power amplifier built in, and then you turn that on, and then that is what powers the speaker inside. So it's a single unit. Passive speakers, which are these that are up there, are really light, and powered speakers are generally much heavier. And we can simplify this even more by having a powered speaker with a built-in mixer or DSP. DSP stands for digital signal processing, and that's basically what these things are doing, except this is analog processing. So you come in here and then you're changing all your settings. This is the processing, and then you're telling it how loud it should be in that speaker. With this, you can have your microphone, plug it directly into a mixer on the back of the speaker with a DSP, and then you can adjust the microphone and the frequencies within this right there. So those are different examples of sound systems. The one that we're going to be using if you ever do any of the events for any other student engagement, like clubs, it's usually going to be this system right here, where we have the source, we have the mixer, and then that goes into the powered speaker, or we go into a system that already has its amplification set up. We usually won't need to set up like an amplifier into a speaker. Something that is added to add more complexity is monitors. So if you have a source and then you're processing amplification output, you can also give the people on stage a speaker so they can hear themselves, and that comes out of the processing step. So we're going to look at microphones now. There's 3 different types of microphones. One of them is not there yet because it's irrelevant to us. But this is a dynamic microphone, and this is a condenser microphone. Dynamic microphones use electromagnetic induction, which is basically like sound waves are traveling into a diaphragm that has like an electromagnetic coil like around it, and then it's vibrating that. Oh, I forgot to explain like what microphones. Dang, I didn't look at my notes. This is the issue with me not reading this. I'm just winging it. So, does anybody know the difference between a microphone and a speaker? Yeah.
There is none.
There is none. Dang it. There's a guy that's smart in here. Okay, so microphones and speakers are basically the exact same thing. You can use a microphone as a speaker, and you can use a speaker as a microphone. The only difference is the direction that the signal is flowing. So technically, if I plug this into an amplifier, I could hear whatever I'm playing out of the microphone because we're sending the voltage back into the diaphragm that's vibrating and causing the displacement of air. Remember the air, sound is air. That's causing the displacement of air, which is creating the frequencies and the tones that we can hear. But if we send, like, the issue with that is these are really fragile, so if I send too much power to it, it's just going to blow up. So I probably don't want to do that. These are designed specifically to displace air, and these are designed specifically to accept the displacement of air. But in theory, they're all the same thing. Some people even use like speaker woofers to mic like bass drums because they take in the low frequencies really well. So dynamic microphones use a tiny little diaphragm that has electromagnetic induction that is causing it to vibrate every time you talk into it or sing into it. Creates AC voltage, and it's sometimes also called a moving coil microphone. A condenser microphone uses electrostatic technology, which kind of has the same type of idea where something is moving to create voltage. Guys, I'm really dying. It changes the distance between itself and the diaphragm inside the condenser microphone, but it's basically a lot more sensitive due to the fact that you need to give it power to move. It's a lot smaller inside and a lot more fragile, so you need to give it phantom power, which is what we do. We basically send 48 volts of phantom power to a microphone so that we can have those sensitive bits work, because they don't work without power. I feel like I did not explain that well. But condenser microphones, just remember that they need to have phantom power. Condenser microphones are good for like miking large groups of people, and then dynamic microphones are generally good, like this one, SM58, is good for a single person up close. The last one is ribbon microphone. We don't care about ribbon mics because they're never used in a live environment. They're basically like dynamic microphones, but in a different way. They use a ribbon. It's unnecessary for us, so we're not going to go there. Polar patterns are basically how a microphone picks up and rejects sound. So we have an SM58 right here. This has a cardioid polar pattern. So if we look at this microphone right there, this is the shape, not to scale really, because the mic would have to be like this big, but theoretically, this is the shape that it's picking up. The cardioid polar pattern has rejection at the back end, which means if you have a singer right here and you're using a cardioid mic, you want the monitor wedge that you're using to be directly in front of this microphone. That way, the built-in rejection of the mic is going to cancel out all the feedback or the frequencies that are coming back from this microphone so that it's not creating a feedback loop. So this is a cardioid polar pattern. And then we have omnidirectional polar patterns. That's like the one I'm wearing right now. Omnidirectional polar patterns pick up from all directions and has no rejection. Bidirectional is good for like if you have two people in a studio and there's one on each side. You can have both singing at the same time, rejecting all like the ambience and the choir from everywhere else. And then there's supercardioid mics, which I don't have one, but basically the reason it's like this is so that you can put 2 monitor wedges on either side, and that's where the cancellation points will be. We won't really need to have to worry about polar patterns too much because for the most part, we're all using cardioids, even these pencil condensers that I have. But you just have to understand that you can't talk into a mic like this. And I think that's self-explanatory, but you'd be surprised. Even like, this is fine, but this is better. Yeah? Proximity effect, something that all microphones deal with except for omnidirectional microphones are the proximity effect. So I'm gonna go back to this mic. Where'd the cable go? Oh, I threw it on the ground. You know, there's me. So I'm gonna take this cable and I have this microphone. You can hear like the depth of my voice coming through, right? We can look at the frequencies again. This is the depth of my voice coming through, all from about 100 hertz all the way up to even 10K, which are like the all those sounds over there. Now, if I move the microphone more than 3 fingers away from my mouth, it's gonna start sounding really tinny. So you can see how even if I just moved it 2 inches away from my mouth further than where it was before, now you're seeing a big roll off in where the low frequencies were. So I have a 3-finger rule. I have all the performers, speakers, take 3 fingers, put it right to the mic, and then that's where their mouth should land. And that gives the fullest sound of the frequency spectrum for your specific voice. If you even put it 2 inches away, you can see that that roll off happens and you can't hear the deep resonance of the voice anymore. We'll go back to this. And that's kind of like a visualization of what I just said. And then this is a pink noise curve. It's not really a curve, it's a line. Is anybody familiar with like white noise, pink noise, brown noise? Ish, maybe not. Basically, these are signal generators that in live sound we use to tune systems. So white noise is basically every single frequency at the exact same decibel level. But the issue with white noise is that's not how humans perceive sound. Humans perceive sound on this pink noise curve. We need low frequencies to be much louder than the high frequencies to hear them as equal across the board. So pink noise is the best sounding to our ears. Do you want to hear pink noise?
Yes.
Okay, let's hear pink noise. Oscillator. You want to see my camera? Look, I got it. Oh, it doesn't work. Top-down view. Bam. Okay, let's get pink noise generator, and then we're going to put that in left, right. So, yeah, I can't like do both the left, right, and okay. This is pink noise. That's pink noise. This is white noise. So we kind of hear the difference. We see how the pink noise sounded a lot fuller in sound than the white noise. It sounds like tss. We use those to tune systems. So if we go back to here, we basically want to go into spaces, live sound engineers. We go into spaces and then play our speakers, and then we're going to balance out the frequencies until we see some sort of pink noise line. So we basically play pink noise, and then we have a microphone that captures what we're hearing, and then we want to match the EQ to make this pink noise curve, which is going to give the full spectrum, the full frequency spectrum available to use in that specific space. Oh, my generator is still playing. Unnecessary. Okay, so let's go to types of speakers. We already did powered versus unpowered, but that's just like a visualization of powered speakers. These have like the little mixer thing we were talking about in the back, and it has a power plug. It's the same one you plug into your computer. Passive speakers have usually what's called speak-on. Speak-on's just like, have you ever like looked at your old sound system in your house and like there's like these 2 wires that you gotta like push the thing in and plug that in? Speak-on's just a connector for those 2 wires, and sometimes there's 4 wires inside that carries 2 different channels of sound. But basically it's the two wires in a different connector. Sometimes you also have a 1/4" plug, like the same guitar cable plug. You can use those for speakers. Then we have the difference between point source and line arrays. So these are point source speakers. They have a set defined spread that they can point to. So basically you would buy a 15-degree speaker to cover 15 degrees of sound, and then you could put them side by side if you wanted to do like a circle of sound, or it's just like to cover a specific area. Line arrays, on the other hand, are very wide and they're adjustable of how wide. And then to get the full coverage of where you are and how far back somebody is, or in a stadium, like where they're seated in the stadium, you can adjust every single level of which, like every single loudness of what each speaker is outputting toward a specific area. And it's very like, imagine like having a spotlight, but like a wide spotlight. That's how line arrays point. And then you can adjust how loud it is for every single level of that. We have subwoofers. Subwoofers are speakers that are made specifically for low frequencies. And because it's so important to our ears, human perception, that we hear those low frequencies, we need subwoofers like this one to give us those low frequencies, because these full range speakers, these are debatably full range, but the full range speakers have equal amounts of highs and lows, but that's not enough for our ears to say that that's sounding good. So we have tops and subwoofers, which are in this line array. These are tops specifically made for high frequencies, and these are subwoofers. And I'm going to show you what the subwoofer sounds like. I'm sure you've all like been in your car and been next to the subwoofer. You know what that sounds like, right? You have a song? Give me a song.
Right now?
Who's got a song? What song?
Non-Stop by Drake.
Okay, so this is our, oh, this is with the EQ in. Oh, I can show you this. Let's see, picture in picture. Oh, dang it. Okay, no, dang it. That. So, remember I did like the high pass before? I'm going to take that out. This is what we sound like in full range. So, you can see how it's like, you hear the lows, and you hear the crisps of the highs, and you hear the middles, the mids. But now I'm going to turn off the left-right speakers. So this is what the subwoofer is doing. So do we know what a subwoofer does now? I think we probably already knew what the subwoofer does. Thank you for the song recommendation. Okay, let's go to mixing consoles and signal flow. I'm at a mixing console right now. There's two different types of mixing consoles. There's analog versus digital consoles. Right here, I have a digital console right in front of me. This is a Behringer X32. And then I have an analog console that looks pretty stupid right next to that. This is an analog console right here. And the biggest difference you're going to see from digital to analog is the fact that there is one channel strip on this, which is the digital signal processing that we were talking about. There's one processing channel strip on this console, and then on this console, there's a processing channel strip for every single channel that we have. Oh, I missed it because I wasn't looking. But this is one channel strip, this is another channel strip, this is another channel strip, and this is another channel strip. And there's consoles like these that have like so many channel strips. But this one, this is a -M32, which is basically the same thing as this. We have one channel strip with a lot of customizable options versus a single channel strip with maybe like half the options for every single input that we have. The difference between using an analog and a digital console is that
How old you are.
Sorry. You know, that's probably fair. But on digital consoles, to assign this channel strip to our channel, we select. So if I select this, I'm not going to waste time doing picture in picture again. If we select this channel, you can see that I have, let's see, what can I do? I'm going to take my voice right now, and I'm going to boost all of the high frequencies in my voice. So you're going to hear a lot of my tss and all that stuff. And then I'm going to put a low cut in so you take out all my lows. So you're hearing basically the highs and the crispiness of my voice. Not too crisp right now. And then I'm going to select this channel, And basically all of that seemed to go away, but it's because now we're affecting channel 2, which is this microphone I'm holding in my hand, rather than channel 1. Does that make sense? On analog consoles it's different because, hold on, let me reset this because now I sound horrible. So on analog consoles, if we take this microphone and I turn it up here, I can adjust all of these settings with the 3 knobs I have. The lows I can turn down, the mids I can turn down, and then I'm left with the crispiness highs. And then I can turn the highs down, I can boost the mids, I can boost the lows. But that's all I can really do. I can't really do anything else. There's an effects thing, but that requires an effects insert. I only have these 3 knobs, high, mids, and lows, to work with on this channel strip. For the same thing on here, I have a parametric EQ, which this one over here, you can still see it. It's a 3-band EQ. We have the highs, we have the mids, and the lows. Right here, this is a parametric EQ. We're going to get into this a little bit more, but basically you can have a lot more control over which frequency bands you can boost or cut. If we go back to this, we also have fixed patch and soft patching. So if you look at these, every single input at the very top of this console corresponds directly down with what is below it. On this, you could plug something into the back of that, and then you could send it to whatever channel you want. That's basically fixed patching versus soft patching. So let's go through signal flow. Very simply, most of the time on all consoles will have gain, which is defined by how much of the input you're accepting into the preamp. The preamp is like basically this XLR connector that it's powering the sound that's coming from your source. So how much of that we're taking in. EQ, which is the equalizations, the high, mids, and lows that we just talked about. Sends, which is where we're putting it. Are we putting it to the left-right speakers? Are we putting it to the subwoofer? Are we giving it to the monitor mix? There's pan, which is left and right. So if you listen to my voice right now, you can hear my voice in the left side, and then you can hear my voice on the right side, maybe, maybe not, or maybe I'm not loud enough. You can hear myself in the right side now, right? I'm feeding back, and then now you can hear myself in the left side. So pan is just how far left and right. Then you have the mute. It's a mute. And then you have the loudness, how loud it is in the output system, the left-right system, or you can be doing it in surround sound, how loud it is in every single speaker that you're controlling. That's what we can do on this console right here. We have the EQ, well, we have the gain right here, we have the EQ, effects, can't really do that because there's nothing here. And then we have the pan, which we can do left-right, also the same way. Pan left-right, pan left-right. And then we have the level right here, which is being sent to the main mix. On this one, we have a lot more things. And that's because, first, it's a lot more expensive, and also because it's digital, so we don't have to take up all that real estate to put all these effects in. It's all like computer circuitry inside. Gain, same thing. Insert, which is different, is basically if you have outboard gear, which I don't know if any of you are familiar with like compression yet or anything. You can buy like physical units, and then you can plug them into consoles, and then you can insert them. Technically, it has a star because you can put it anywhere in the chain on a digital console. And you have a gate. Gate is like an automatic mute. We'll get into it a little bit later. Dynamics is compression, which we'll also get into later. And then everything else is the same. But you can do a lot more with all those things. So let's go through what gain staging is. When you are setting up for a show and you're doing a sound check, you want everything, all your speakers to live at unity, which is 0 dB, and that's going to give you the most headroom. Headroom is like how much extra space you have above where you can push your speakers and the level. Does that make any sense? Do I need to explain it better? Basically, if you have the speaker at a certain volume set by the manufacturer says that when you set it at that volume, you have enough space to go up and you have enough dynamics to go down. If you boost it too high, it's going to start distorting because the speaker's not designed for that. Having the correct loudness for the capacity of every piece of equipment. So your mixers and your speakers, they all have to have a correct gain structure for you to be able to properly use a sound system and for it to sound good. Analog unity, so on this, analog unity is 0 dB, and you can kind of see that right there. There's a 0 right in the middle. You'll see these when you play with the mixers. In that room, we have all these like mixers set up. You're just all gonna touch them and then do things. Hopefully not break them, because that'd be unfortunate for me. But unity is 0, and you can see that on the fader right here, you have 0 dB. On digital consoles, we measure decibels differently. So what outputs from this console over here is 0 dB signal, but to get that same analog 0 dB signal on a digital console, you have to mix at negative 18 decibels. So that's just something you don't really need to know, because you'll see it going red when it's wrong. But analog consoles, you're mixing at 0, digital, you're mixing at negative 18. But use your ears. It's important to use your ears. Sound engineering is all about ear training. Let's go through signal processing, all the different things. I'm going to go through really fast what we just learned in that signal chain. First, we have gain. I explained it, how much you're letting in from the preamp, from the source. So the source is plugged into the preamp, and it's being sent power, and then now you're telling it how much you want in your system. Insert outboard gear. I explained that. Gate. So I'm going to show you what a gate looks like. I'm going to take my SM58. Oh, now we're coming in two different places. And then I'm going to show you this split screen. So I'm going to look at the gate area, which is this, and you can see the sound of my voice coming through. That's the level at which my voice is hitting at an average, not at every single frequency. It's averaging all the frequencies. That's where my level is hitting. And a gate is basically like an automatic mute. So if I turn this gate on, and then I move this, you can see that when I'm talking at my normal volume now, the threshold is above where I was originally talking, so it's not unmuting me. If I lower that threshold down to where I was talking again, you're going to start here like click in and click out based off of how loud I am. And the threshold is basically telling the console when to unmute. So if you set the threshold of a gate down here, it's going to pick up every single sound that I say, but every time I'm done speaking, it's going to mute it. And then you can see that red bar fill up, right, on the side. So what's helpful the reason why we use gate is to reduce our noise floor. Noise floor is how much signal noise or air noise there is in the space. So when you have open mics all the time, you're going to be hearing the wind blow if you're outside, or even if you're inside, you'll hear the air conditioning humming, or you'll hear the steps of people walking by, because it resonates through the entire mic stand. So by putting a gate on something, we're allowing us to have more freedom with what we spend our time on, instead of muting and unmuting mics every time we hear bad noises. Does that make sense on what a gate is? Mm-hmm. Equalization. So equalization is basically the ability to modulate the different frequencies within the frequency spectrum. So I'm going to go back to split screen over here, and I'm going to show you once again the EQ. You already saw the EQ like multiple times at this point. I'm going to switch over my mics, and then we're going to go to our EQ page. This is a parametric EQ I showed you before, the high, mids, and lows. The parametric EQ allows me to specifically choose what frequency. You can see where my dot is moving on the right side. So if I want to boost the frequency of 1,000, 1K, which is 1,000 vibrations per second, I'm going to push the gain up, and you can see that it's a bell curve. So it's also pushing the frequencies from like 200 all the way to about 6K. And if I want to tighten that up, I can change the Q, and then that will boost only that certain area. EQ is really important for different instruments and different sounds, different vocalists. Sometimes people don't have a really strong low-end voice, so it doesn't sound full, so you might want to boost anywhere around 400 hertz. 400 hertz, which is going to give them the depth of sound. Do we understand EQ, maybe? Possibly. So, dynamics, which Sean wanted to know and I tried to explain earlier. Dynamics is basically the ability to compress a sound. So when you have an input signal, I'm going to go back to this one. When you have an input signal here, I'm going to lower my EQ back. When you have an input signal, it comes in and nothing is happening to it. The louder I am, the louder it gets in the system. the quieter I am, why are we panned? The quieter I am, the quieter it's going to get in the system. But if I want to control how loud somebody can get, or I want to kind of do this to them while I'm mixing, like if somebody's getting too loud when they're singing, then I have to push the fader down a little bit, and then I have to bring them back up when they're being quiet again. You can solve that by using compression. So you take this threshold, just like the gate, and then we're going to bring that to about where our normal speaking voice is. So you can see my peaks are coming in around wherever I just said that. It's like negative 16 decibels. So those are where my peaks are. But now, when I go really, really loud, you can see that anything above that threshold, anything above that green line is being squashed down. So it doesn't sound like I just broke the system. But if I turn that compressor off and go really, really loud again, you can tell how loud it is, right? And then if I put the compressor back on, it basically is one, a safety measure, and also, number two, it controls the audience experience and how they're perceiving the singer or the speaker. That's compression. Did we kind of understand that? Do we want to go into compression ratios? Does anybody care about that? Yeah? Okay, so, well, I had one yes, unfortunately. So, the way compression works is 1-to-1 is no compression at all. It's not that complicated of a topic, ratios, but basically if you have this 1-to-1 signal, when you send it 1 decibel, and you have a 2-to-1 ratio, every 2 decibels that you send over the threshold, it's going to squash that down to 1. And then every 4 decibels in a 4-to-1 ratio that you have, it's going to squash that down to 1 decibel. Does that make sense? It's basically how much compression is happening. Kind of? Okay, well, we'll see. Sends. Sends is like where you're sending things. You can send things to the left, right, you can send things to the monitor, you can even send things to effects. So if I take this, I have effects sends. I'm not going to show you this, but it's not that hard. So I have my channel, and then I can send it to a specific bus, and then that bus can have a reverb link to it. This is a hall reverb that you can also change the settings of. This is a send, because I'm sending my signal to a bus, which is like a collection of channels and signals, and then that's sending it to an effects processor, which is sending it back to an effects return. This is kind of complicated, guys. But if you kind of get it, you can send things to different places. Pan, left, right. So when you hear a live concert, not everything is in mono. Not everything is coming out of both speakers, or however many speakers there are in a space. Not everything is coming out at the same level. So when you have a concert and you're looking at a band, there's usually like a drummer in the middle, or keyboards on the right, brass anywhere. This is just like an example of how somebody might pan somebody or some band. So you can see that the vocals, the kick, the bass, and the snare are all centered because they're the main focal point, and the kick and bass are mostly important to keep at center because they're what grounds the entire mix, and they're all the low frequencies. You usually don't want to be panning low frequencies, and it also doesn't work too because subwoofers are built omnidirectional. Remember the polar patterns we talked about? Subwoofers are always omnidirectional unless you do some specific tricks to cancel it out with phase cancellation. But they're most of the time omnidirectional, so you want to keep the bass, snare, and kick. Snare can be off a little bit, but bass and kick are usually very centered. And the vocals, depending on how many vocals you have, if you have one vocal, you can keep it centered. But if you have two vocals, you can like slightly pan them from side to side, just so that the human perception of what's happening on stage is also translating to what they're hearing. Does that make sense of why we pan things for the stereo? I don't know what else to say. Mute. It's a mute. So we're going to go to loudness, which is how loud it is in the master system, or how loud your sends are to like monitor wedges and stuff. You can also control the loudness of the entire system itself. So like you can see here, I have a master fader, and then if I had monitors, they're on these faders. So each monitor has a different fader, but I can also choose how much of each thing is sent to each monitor. Loudness. Mixing techniques. Oh dang. Mixing at unity I talked about. Most of the time we want our faders to start at unity. So when we do a sound check, all our faders should stand right here. And the reason for that is because of the amount of resolution we have within the fader. If you move the fader when it's between -5 and +5, it has a very high resolution, which means the small moves that you make are making even smaller changes. But if you go down to past -10, you can see how like the scale kind of gets squashed down. It's a lot more low resolution. So this is where you have the most control over your mix when you're mixing, and that allows you to have control over the sound. Did that make any sense? What else? Should I read the slides? Then go through each channel and signal. Set at a sound check and does. Oh yeah, gain is set at sound check and then does not change throughout the rest of the event. The reason for that is if you change the gain, you change how much you're sending to the monitors and the subwoofer. So if you already set the levels of how much a band member is hearing their instrument in their ears, you don't want to change their gain because then it gets really loud for them if they're at a good volume. If you're mixing just for the front of house, you're going to be changing the fader levels, which are right here. You wouldn't be changing the gain, which is this now, because that changes how much signal is coming in from the board, if you remember. And then this is changing just how much you're hearing in the space. Stereo imaging. This defines where all sources are within the space. I just talked about panning. This is a good example, which you already saw. I think, let's see, do I have time to create a mix for you? Maybe I do. So I have this, don't stop me now. Yes, right? Probably. I'm going to show you like the basics of how I would start creating a mix. Let's see. I'll give you split screen. Where's black? There. So I'm just going to play this right now. It's a quick multi-track. And I'm just going to show you how I would go through each channel for like a minute. And like show you how I would live sound check something. So I'm going to start with the vocals. Everything's up, so I'm going to bring them all down. And you can see that, this does absolutely nothing.
And the world outside it
Give me a
is
second. Save, logic, settings, audio, output device, X USB, apply, save.
Okay. I'm gonna have myself a real good.
So I just took out the effects because I sent it to effects before. But basically, I'm going to go through here. I'm going to set the gain. So whatever the right volume sounds like in this space is where I'm going to set it. Then I'm going to go to EQ. And then I'm going to, for this space, I think I'm going to squash a little bit of the highs. And then I'm going to also take down some of the resonance that was here. He's going to start singing.
Cause I'm having a good time.
Just so it's a little bit more crisp. And then I'm going to go here. I don't really need to set a gate because this is recording, but theoretically when all the mics are sitting there, that's when you would set your gate so that you can pass the noise floor. I'm going to go to the compressor. So I'm going to look at where his vocals are really landing so that if he gets much louder at any point, it gets squashed down. So this is about where he is, and you can see that it's like getting a little bit squashed right now, so we have full control over the mix. I don't need to send it anywhere, so I'm going to move on to the kit. I'm going to bring that to Unity. I'm also going to send this to the subwoofer because I want this in the subwoofer. I don't really like how clicky the kick is, so I'm going to cue out a little bit of the high frequencies. And then the kick is something that people can abuse, so I'm going to put a compressor on that. That's exactly where the kick is landing, where I want it to sound. I'm also going to bring the ratio down to a 6. Oh no, that's a 5. Let's move on to the snare. So if we solo this, you can see we're hearing other drums in the mix and we're hearing cymbals. If I really only want to hear that snare, you can see where that snare is hitting on the graph, right? I can even give a high shelf to all of these so I can, not a high cut, high shelf please. Just so all those cymbals aren't coming out. And then I can go to the high point of where the clickiness of the snare lies. see how like the sound is like being shaped as I do this? I'm also gonna bring up the gain because I forgot to do that. And I can bring these back. And then you understand like what's happening, kind of. I'm basically shaping each channel strip, moving on to the next thing. And this would usually happen during sound check. You'd go through each individual source, and then you would shape the sound. So again, you select, and then you would go here. But again, this is the same on analog consoles, except that you don't have to do the selecting. It's just everything's in a line. So I set the gain. I want my pianos to be a lot crispier, so I'm going to bring this. I want a brighter piano sound because I personally like brighter piano sounds. And I'm also going to take down where we're peaking over here. Bring down this a little bit. And another thing we can do at this point is we can send it to things. So if I can put this in a space, I can give it some reverb. Or I can even send it like delay. I'm doing a tap tempo right now, so the delay matches. But that's basically how sound check happens. Do we kind of understand that? It was kind of fast, and it was kind of, I don't know if you got any of that, if the screens are too small. How is that? Good, bad? Okay, fair. Let's go back here. So live setup and troubleshooting. Basically, before you go to an event, you want to know the space you're performing in, the space they're performing in, the space you're going to be mixing in. You want to know how echoey the room is. So you want to like go around clapping a lot just to see if you need any noise dampening or how bad your experience is going to be, because the more echoey it is, like in the chapel, sometimes the echoey is good. Other times it just echoes the feedback and then I start crying. So you have to look at where the power is, because you need power unless you're doing everything from a generator. I don't know. You need to know where to plug things in. Are there in-house speakers? So like if I was doing a thing in this space, I know there's speakers right here. So I can use these speakers instead of having to bring my own speakers. These are just things that you might not need to think of if you're working any of these events on campus, but like a sound engineer would think of those things if they were going out into the world and doing a show. System setup. Sometimes when you're on a big show, you set up the entire sound system in a warehouse and test the system to make sure it all works before you load it out onto trucks and then bring it to the event site. So system setup in a warehouse or testing site is really important to make sure that everything works and you're not bringing dud equipment to the place. Equipment preparation. This is an example of some paperwork. It's really complex, but basically you have like all your inputs in a list, all your outputs in a list, who's got monitors, where the monitors are going to be. The stage plot's not actually on here. And then these are like digital snake units, where everything's plugged in, which channel. Knowing and having an exact plan to do a show is how you get things done efficiently and how things happen right and have the least amount of issues. But issues are always going to be apparent, so you need to know everything that we just covered to be able to fix those issues. Feedback avoidance is something that's fun. I have a microphone over here that I'm going to swap out, and I'm going to give you some feedback if you want to hear some feedback, right? Everybody wants feedback. Where's this? Okay, I'm just going to plug this one. So this is a condenser microphone. Remember I talked about how condenser microphones need phantom power? If I plug this in here and we look at the meters on this channel, let's go back to this split screen view. Oh. So if I go back to, the information showed up. Well, now you know what my shutter speed is at. If we go back to right here, I just plugged it into this channel, and then we look at the EQ of this channel, just so we can see any noise. I don't know why I just clapped toward the camera. I'm going to clap toward here. You can see that I'm clapping, and nothing is coming through this specific microphone, because that's the RTA we're looking at. RTA stands for real-time analyzer, which is looking at all the frequencies from a specific source. I'm clapping, nothing's happening because we did not turn on phantom power. On analog consoles, we have usually a single button that turns on phantom power for the entire system, or like really, really large analog consoles have individual phantom power buttons because it takes too much power to power the entire console when you don't need it. So there's a phantom power button right here. It's not pushed in, and I can't because you need like a pin to push it in, but we're not plugged into that. So we're going to plug it into, we have it plugged into here, and we have individually assignable phantom power, so we're going to hit this button right here, 48 volts of phantom power. But really important, it's going to pop, so you want to have the channel muted before you activate phantom power, and then you're going to activate phantom power, and you're going to see that giant pop. that we saw but didn't hear, right? And you don't want that giant pop going through your sound system, because then people are like, what is that? You break my speakers. It's actually probably going to be me doing that if that happens. These are the mics we use for acapella. So that exact thing that I just did is something you're probably going to have to do if you work any of the acapella shows. Now I have that on, and you can see that I'm getting signal in here now. I'm clapping and you're hearing the signal. Now that we're sending it power, it has enough energy to take in the sounds and vibrate at the specific frequencies that we're sending it. So if we look at this, you can see that even if I'm standing over here, it's picking me up. And when I'm standing all the way back here, it picks me up as well. So condenser microphones are a lot more sensitive than dynamic microphones. They also are a lot better in high frequency reproduction. So what was I talking about? Feedback. Okay, so do we understand what feedback is? Is anybody like confused on what feedback is? Basically, oh well, that was a good example. Basically, when you put a microphone in front of a speaker that's outputting that microphone, it creates a loop of sound that is, I would say, unpleasant to listen to. So I'm going to take this condenser microphone, put it in front of the speaker, and don't worry, it's not going to blare. You can, don't worry about that. I'm just going to put it up a little bit, and then once you start hearing feedback, didn't hear anything yet. That's magical. Oh, there's feedback. Push it a little higher. So this is feedback, and then something that we can do to avoid feedback is called ringing out mics. So if I know that there's feedback right here, I can push this to where it's feeding back, which we can see on this graph is about 500 hertz. So I'm going to go into my parametric EQ, and then I'm going to, why are all these backwards? I'm going to take down this a notch, and you can see there's another feedback frequency. So we're going to try to get that back, and then we're going to notch that out. And you can see with these notches I'm making, I keep pushing the fader, and I'm getting more and more headroom as I notch these things out. That's called ringing out mics. The reason we ring out mics during like a sound check is so that we avoid feedback during the show. Does that make sense? Yeah.
What happens if you need those frequencies?
So here's the, usually,
Uh-oh.
so usually when you need those frequencies, you can compensate that by only EQing them out of the monitors or whatever speakers are closest to the stage. If you have like multiple speaker sets, like if you have mains and then you have delays, you can take their frequencies out of the mains and then overcompensate with the delay speakers. Another thing we have to always think about in system setup is having the speakers in front of the microphones. So in this scenario, the speakers are behind the microphones. It should always be speakers here and then microphones and performers back here. That way the chance of it feeding back from here, bouncing on the back wall and then back on this back wall and then back into the microphone, it's a lot of area to travel and it's unlikely that that's going to happen. What else do we have? Mixing different types of events. Let's see, what's our projector looking like?
It's slow. I'm sorry, I have it on a timer because people leave it
It's
on.
also 7:04.
7:04. Hey, yo. Oh. Okay, does anybody have questions so far? No? No? Because I have questions. I'm confused on what I'm saying. Mixing different types of events. Let's just imagine. Concerts, music performances, musicians, instruments, a cappella, soloists. That's all like mixing and balancing between musicians and instruments or soloists to group and percussionists. Then we have corporate events, which are you're focusing on the clarity of the audience understanding for maximum engagement among the speaker and the audience. The All College Symposium, as I mentioned before, is an example of a corporate style of event, except they did it bad. They had nobody like running the sound, and then sometimes the person would be way too far from the mic and you couldn't hear them, then you'd be like, what? And then they'd ask questions, and then like the speaker was also like behind the microphones at some point, so there was some ringing. not the best thing. Searching for source. There's the source. If you see the text over there, it says Ethan refuses to do corporate events, so there's no picture here, because I hate corporate events and they're boring. So that's why I don't do corporate events.
Really good.
They do pay really good, but when I get bored, I fall asleep, and I've fallen asleep before. And the last one I'm going to cover is theatrical mixing. You don't need to listen to this here. But theatrical mixing is balancing the levels of multiple actors for consistent and clear lines so the audience can understand. Managing the balance between the music. The band is playing, and you need to balance the level of the band at every single point in the show, and the singing that somebody, like a soloist or the entire ensemble, you have to balance all of that. Controlling all the intensity of all the sounds and effects set by the sound designer to maintain the consistency of the show and the storytelling that affects how the audience perceives the show that they're watching. Line mixing is a technique in theater that we use. It's the standard method of mixing on Broadway, off-Broadway, any of those shows, regional theaters. Basically, line mixing is only having the mics being used open at the time that they're being used, and then once they're done speaking, that mic goes off. This is a video of me line mixing. This is Chicago. So you can see, after every single actor has their line, their microphone turns off. And we mix on VCAs. So these 8 faders, I press the button, and then in the next scene, all those faders are for different people. So only one fader up at a time. Sean thinks this is crazy. So like, as a sound engineer right now, I heard that there's a pop in somebody's mic. I looked on the meters for which one popped. I saw that it was channel 4 or whatever it was, and I put that down because I don't want any more popping to occur. And then you can see that because these are their monitors on stage, I'm boosting the tracks in their monitors so they can stay together with the music. And balancing the audience's experience and interpretation of the show. So that was a lot. That's all there is. How was that? Is everybody dead from listening to that? No? Was that good? I tried to go fast. I was trying to stay 30 minutes, but it's been an hour. So we have in second floor, I'm gonna leave this console here and I'm gonna flip it like that. So there's going to be 4 different stations. I have a station over there with dynamic microphones that you can play with, adjust the EQ, listen to how dynamic microphones respond to. There's mixers there and there's speakers there. Then I have that exact same setup with condenser microphones and a shotgun microphone, which is a type of condenser microphone that basically has like a spotlight type of pickup pattern. So it's a cardioid, but it's a long cardioid. And then we also have a station where I have a new digital mixer, which is a box that has no faders or controls, and it's all tablet controlled. So that's like what I have right here. You can see that my tablet's connected to this. And then if I go to what we're looking at right here, you can see that this is moving that. So I have tablet controlled mixer in there, which is going to be what's running all the a cappella concerts from now on because I'm tired of dragging this thing there. So that station also has the ability for us to learn how to set up the sound system. Nothing's plugged in yet, everything else is. And then I'll have this station open if anybody wants to like play with the faders and mix Don't Stop Me Now. I don't know why, for some reason I thought I forgot the title and I was like, wait a minute. Okay, are we all good to stand up and like move?
They're gonna move. They're gonna go to your favorite room.
Okay, so we'll walk in there really quick so I can show you which each station is.